Okay, my kids are playing on the trampoline with the sprinkler. It's hot. It's about 95 degrees here, so I thought I'd do a video while they're playing. First, I want to revisit this heat curve because there was something I forgot to mention. And that is at these 2 points where we have, and just so we remember, this is solid, this is liquid here, and then we have gas up here. Okay. At those 2 points that I've circled in the highlighter, those are at equilibrium. What does that mean? Okay. That means, for instance, at the solid to liquid phase transition, we have solid turning into liquid, liquid turning into solid at the exact same rate. Okay. Melting and freezing are occurring at the same rate. So that is an equilibrium process. Same goes for here, but it's liquid to gas. And those are just backwards and forwards arrows to indicate that the process is occurring at the same rate. Okay. I just wanted to clarify that. And we're going to zoom in on both of those, or at least on the liquid to gas phase. We're going to talk about that in a little bit more detail, that transition. So we are going to talk about vapor pressure. And vapor pressure is given the abbreviation, usually P VAP. That's just P with a subscript VAP for vapor. Okay. If we have a flask, let's see if I can draw a really bad picture of a flask. I guess now that I'm using a computer I can cut and paste, but oh well. So there's our flask, and in it we're going to put some H2O liquid. Now, if we set this on a sunny windowsill, we all know what's going to happen. That H2O liquid is going to turn into H2O gas. Okay, the water is going to evaporate. And we have a cork on it. So what happens is the liquid water becomes gaseous water. But does it all become gaseous water? Well, if you look at it after a while, you'll see beads of condensation forming on the inside of the flask. Okay, and that is an indication, whoa, that was fun. That's an indication that the gaseous water is turning back into liquid. So we can write a chemical equation just like I had up there, kind of. That the liquid water is turning into gas and the gas is turning into liquid. Okay, and that is what we call a dynamic equilibrium. If you think about a gymnast on a balance beam, she's in dynamic equilibrium. May not look like she's doing very much, but she's constantly falling left and right and checking her balance. The better she is, the less you'll notice. Okay. And what this dynamic equilibrium really tells us is that the rate of condensation, or I'm sorry, rate of evaporation is equal to the rate of condensation. Okay, and that P VAP, the vapor pressure, that is just the pressure, the partial pressure of a gas above the liquid. Okay, and this is at equilibrium. Whoa, what happened there? At equilibrium. So do all liquids have the same vapor pressure? Well, no, not at all. If you think about spilling some acetone, some fingernail polish remover on the floor, and spilling some water on the floor, same volume, same temperature, right next to each other, what's going to evaporate first? The acetone is going to evaporate first because it has a higher vapor pressure. Okay, and so we can say that lower IMFs give us higher vapor pressure. Let's just do PVAP. Why is that? Well, the lower the intermolecular force, the easier it is to rip those molecules apart, and therefore the more readily it will evaporate, and that will give us the higher vapor pressure. Okay, lower intermolecular force just evaporates faster. So, acetone, and we can draw the structure for acetone again. I'm just going to draw these CH3 groups. We don't really worry about them. What we're interested in is the C double bond O versus water. The water, the acetone will have the higher vapor pressure. Higher, and I didn't look up the numbers, sorry. Higher vapor pressure. This will have lower vapor pressure. Because, of course, if you remember, we have hydrogen bonding here. Here it's just dipole-dipole. Dipole-dipole is stronger than some other intermolecular forces, but it's not nearly as strong as hydrogen bonding. Okay? Let's see. And higher the temp, the higher the vapor pressure. Well, that just makes sense. The higher the temperature, the more readily something will evaporate, so the more gas we will have, and the more easily it will evaporate. So now I want to talk about something really, really exciting, watching water boil. Okay? And we're going to talk about what we call the normal boiling point of a liquid. I just heard one of my kids scream, ow. I'm not going to check. Okay. Now I can't think. Anyway, normal boiling point of a liquid. So let's just talk about water because it's obviously what everybody knows. And you can do this at home next time you make top ramen. Let's just take 2 beakers. It could be a pot, doesn't matter. Put some water in there. And we're going to put a flame under them. Okay? We're going to put kind of a low flame under this one. And then under the other one, we're going to have a hot, higher flame. Okay, so let's talk about the one with the low flame first. And this could also just be when you're starting a pot to boil. What you'll notice is just some little bubbles starting to form right here. Okay, just at the very, very bottom. But then they just pop. Okay, and then they don't really pop; they just collapse in on themselves. And I swear to God, you could watch this at your home. It's super exciting watching water boil. Okay, I just gotta add that. And why is it that they pop? Well, what's pushing down on the surface of this water? Atmospheric pressure. Okay. And if we think about the beaker of water, down near the bottom, down in this region here, it's pretty hot. But as we go higher, it gets a little cooler and a little cooler until it's, basically just cold water at the very, very top. Of course, it will mix as we go and it will heat up, but I'm talking about initially, okay? So what happens is we get a little bit of H2O gas inside of that bubble, and that bubble is all H2O gas, okay? It's just water vapor. Water vapor forms a bubble, it rises, and as it rises up, it cools off, and then this atmospheric pressure crushes it, okay? But if we go over here to the hot flame, that doesn't happen. The bubbles rise to the surface, and they pop, and that's at a full boil. But we still have pushing down PATM. We still have the atmospheric pressure pushing down on the surface. So we can say in one instance that PVAP of H2O, let's call it partial pressure of H2O, is less than the atmospheric pressure. Okay, as long as it's less than the atmospheric pressure, no boiling. When we get to this point, PH2O is now equal to PATM. Some of you might have maybe wanted to say greater than. That's a situation we call superheating, and that can cause violent boiling that chemists call bumping. Okay, you superheat the water. There's reasons for that. It gets above the boiling point, and it will boil violently all of a sudden all over the place. So, normal boiling point is when is the temp at which PVAP of a liquid is equal to 1 atmosphere. 1 atmosphere. Okay, that's what we call the normal boiling point. Water is at a boil, however, when PVAP equals vapor pressure. I'm sorry, PVAP equals atmospheric pressure. So if we were going to boil water on top of Mount what's that big one? Everest. Thank you. Mount Everest. The pressure up there is way low, so the water boils at a much cooler temperature. You want water to boil at a higher temperature than the normal boiling point, you got to go down below sea level. Death Valley, Salton Sea in California. You could also go to the Dead Sea. That's the lowest point on Earth. All right, that's enough for now.